Hi everyone. What we're going to be working on in today's video is incorporating what we already know about the first derivative of a function, namely that if the first derivative's value is positive, a function is increasing, and if the value is negative, the function is decreasing. So we're going to incorporate that into what you're about to learn with the second derivative of a function, which will tell us about the concavity of a function. So remember, a function is concave up when it looks like this, where I say, if it was a bowl, it could hold soup. It's concave down where the soup would fall down if that was the bowl. Just indicates the way it's facing. So let me give you some information. We'll walk through some notes together, and then we'll actually do some problems. So on a given interval, if the second derivative is greater than 0, in other words, if it's positive, the function will be concave up. And if the second derivative is less than 0, meaning if it's negative, then the function will be concave down. Okay? That also gives us information about maximum and minimum values, local max and mins. So if the first derivative is 0 and the second derivative is positive at a particular point, then that particular point would be a local minimum of the function. And if the first derivative is 0 and the second derivative is negative at a particular value, namely c in this example, then we would have a local maximum at that of that function. Okay? Here again, you see concave up and concave down. This page just reiterates what we just talked about. And what we're going to be doing with all of this information is we're going to be sketching graphs. And we are not going to be using our graphing calculators. We're going to be using what we know about first and second derivatives, as well as domains. We're going to be finding the critical values using the first and second derivatives. We'll also think about our horizontal asymptotes and our vertical asymptotes, and do we have points of discontinuity and y-intercepts and x-intercepts and all that we know about graphs. Okay? And again, we've talked about this, but that point of inflection is the exact point where a function changes concavity. So maybe it changes from being concave down to concave up, or maybe it changes from being concave up to concave down. All right, let's do it. Look at the example that I have for you. And what we have to do here is we're going to have to find all critical values of the function so that we're going to be able to graph this. So we know when we calculate the first derivative and set it equal to 0, we will find values that are called critical values, and that will allow us to test where the function would be increasing and where it would be decreasing. So let's do it. We're going to take the first derivative of this function, and we get 6x squared minus 6x minus 12. We're going to set it equal to 0 and solve. Hopefully you see that we have a GCF that we can pull out. So we've got x squared minus x minus 2. We're going to factor this. Hopefully real quick you can see x minus 2, x plus 1, which means that our critical values are located when x is 2 and when x is negative 1. Okay, so what are we going to do with this? Well, we're going to use these values and test to the left and right of them. So we're going to put negative 1 here, that's our first critical value, and 2 here. We have to put them in numeric order. And we're going to pick a value to test. So a number to the left of negative 2, of negative 1 would be negative 2. Between negative 1 and 2, I think 0 is an easy one to drop in there. And bigger than 2, let's go with 3. Now, I believe this is the easiest form to use because we can just look for signs. We don't actually have to do the calculation. So when we substitute negative 2 in here, we get a positive, which is the 6, times a negative times a negative. And a positive times a negative is a positive value. When we substitute 0 into this, we get that positive times a negative times a positive. And again, I'm just dropping 0 in here and just looking at what the sign would be inside there. But you multiply those together, you will get a negative. And when I drop a 3 up here, I get a positive times a positive times a positive, which means the sign of f prime in those particular regions would first be positive, then be negative, then be positive. What that tells us is that the function is increasing on this domain, decreasing on this domain between -1 and 2, and from 2 to infinity, it will be increasing. Okay, so let's scroll down a little bit more, and so we can identify where the function is increasing. So it is increasing from -infinity to -1. Okay, -infinity to -1, union from 2 to infinity. It is decreasing only between -1 and -2. I'm sorry, -1 and 2. Sorry about that. And if you think about this, if it's increasing and then decreasing, that means that the point located at -1 would be a maximum, wouldn't it? A local max. So our local maximum will be located at -1 something. We have to find that y value. And we would have a local minimum. Look what's happening here. It will be decreasing and then increasing once it gets to the x value of 2. So decreasing turns into increasing. That would mean we'll have a local minimum at 2 something. And so now we would just have to calculate f of -1 and f of 2. I'm going to save you the time on that. This would be 19. So we have a local maximum at -1, 19. We have a local minimum at 2, -8. Okay, so you'd be able to use a baby calculator for that. So that's kind of all of the information that we get from the first derivative. So I'm sure you know what's coming. Now we're going to go ahead and take the second derivative, and we will now get information about the concavity of the function. So I believe it is easiest to use this version of the first derivative, and we're going to also set that equal to 0. So we get 12x minus 6. That's an easy solve. Move that 6 over. Divide by 12 and reduce. So we'll get x equals 6 over 12, which is 1/2. So what that tells us is we only have one place where our concavity might be changing. So I don't even need this value right here. The critical value that we just found was 1/2. And of course, we're going to do exactly what we did on the first chart. We will pick a value to the left of 1/2, and we will pick a value to the right of 1/2. And now we will test them in the second derivative. So if we drop a 0 in here, we wind up with a negative value. If we drop a 1 in here for x, we wind up with a positive value over here. Here's what that tells us. When the sign of, this should actually say second derivative, it should be double right there. The sign of the second derivative is negative. Our function is concave down. When the sign of our second derivative is positive, our function is concave up, meaning that this point right here is a point of inflection. Point of inflection. So let's look at the interval where the function is concave up. It would be from 1/2 to infinity. So it's going to be like this. So from 1/2 to infinity, our function will be concave up. From -infinity to 1/2, our function will be concave down. And our point of inflection is 1/2, and then we would have to put the 1/2 back into our original function, into f of x. I'm going to save you the time this time, and it's going to be 5.5. So that gives us the exact point of inflection. Okay, whoops. Other things we should be thinking about. What is our domain? Well, in this particular case, because we have this function that's just a polynomial function, our domain goes from negative infinity to infinity. So negative infinity to infinity. We know that it's increasing without bound, so there's not going to be any horizontal asymptote. We have no denominator or excluded values to give us a vertical asymptote or a point of discontinuity. Our function, we can easily see our function has a y-intercept at 12. Okay, so we have a y-intercept at 12. Okay, and in terms of the x-intercepts, sometimes we're going to be able to factor, sometimes we're going to use synthetic division. Right now, I'm just going to skip that. Won't get too complicated here. But let's go ahead and let's try to sketch a graph with everything that we know. Okay, so first off, I have this y-intercept at 12. So 0, 12. We know our function is going to go through that. We have a maximum, a local maximum at -1, 19. So, of course, we're just estimating here. Okay, we have a local minimum at 2, -8. So 2, let's call this -8. And we have a point of inflection at 1/2, 5.5. So 1/2, I'm going to call this 5.5. 1/2, 5.5. Okay, and we know that our function is, again, I'm going to scroll up here. We know that we are increasing until we get to -1, decreasing until we get to 2, and then increasing. We know that we are concave down until we get to the 1/2, and then we are concave up. So a general sketch would look something like this. Increasing and concave down, looking like this. Now it's going to turn here and it's still going to be decreasing, but it's going to be concave up. And it's going to look something like that. Okay, so we could have been a little bit more accurate if we had calculated the zeros of the function. We could have been a little bit more accurate, but I think that was plenty for right now. So we did all that just from prior knowledge about functions and from first and second derivative. Okay, we're going to do one more. Why not? This is fun. So here's our second problem. And what I'd like for you to do is I'd like for you to go ahead and calculate the first derivative and put your critical values here and see what you get. See if you can fill out to this chart and then restart the video. Okay, so you go ahead and do that, and let's see if we come up with the same values. Okay, how did you do? Hopefully you got the same values as me. Okay, -3 and 1, we tested some values. It's increasing, then decreasing, then increasing, which, by the way, should make sense because it's x cubed and it's positive. So you know that kind of looks like this. Okay, go ahead and write your intervals. Pause the video. Do this next part. All right, did you get the same intervals as me? And did you get the same local max and local min? Hopefully you did. That was just substituting -3 in to get the 14 into the original function and 1 to get -18. Okay, so let's see if you can go ahead and take the second derivative and get some information from that. So I would go from this version of the first derivative, calculate the second derivative, the critical values, see if you can fill in this table, and do the concavity up and down and locate the point of inflection. I want you to do this whole side. So pause that video. You got this. All right, let's see how you did. That was a simple solve, I hope. It was an easy second derivative. We only got -1. Hopefully when you substitute it in, you saw when you substituted -2, it would be negative, which would indicate that the function was concave down. And of course, when we substitute 0 in, it's concave up. Here are the intervals for concavity. Here is our point of inflection. So let's continue and let's think about what else do we know. Well, this is another one where the domain is from -infinity to infinity. We don't have any asymptotes or points of discontinuity. I'm not going to worry about the x value for this one again. Why, we'll be okay with that. And very simple, our y-intercept, that's an easy one because it's always the constant from our original function. So our y-intercept is at -13. So why don't you go ahead and see what you can do regarding a sketch for this. Okay, pause that video. Okay, how did you do? We had our local max here from -314. We had our local min here at 1, -18. We had our point of inflection at -1, -2. Notice I made a big giant dot there, okay, in a different color. That's what I'd like for you to do to indicate that that's a point of inflection. And of course, we knew it was concave down up until this pink dot, this pink point, and then it was concave up for the rest of it. And it's just going to continue forever and ever to positive and negative infinity. Oops. Okay, everybody, I hope this was helpful. Have a great day. See you in the next class.